And this is the video for 8-1. So yesterday we did this problem, 51, where it says the first and third terms of an arithmetic sequence are -1 and 5. What's the sixth term? So just to remind you, ready? If you're in the building, you weren't here yesterday, you didn't see all of this, you would set this up with a T-chart. So the T-chart would look like this. N, I'm going to call that A sub n because they're telling me it's arithmetic. Like, it doesn't really matter what you label the column heading, but if I know it's arithmetic, I'm going to call it A sub n. If I know it's geometric, I'm going to call it G sub n. So it tells you the first term is -1, and the third term is 5. So then you would say, okay, let's find the second term, the 0 term. They ask you for the sixth term. But if it's arithmetic, it's going up at a constant rate. So the difference between -1 and 5 is 6. So this distance, half of it would be 3. So this would be a +2. Then 3 less than -1 would be a -2. Then keep going up by 3. 8, 11, 14. The sixth term is 14. This is a sequence. Okay? When the terms are separated by commas, it's a sequence. When the terms are separated by addition or subtraction signs, it's a series. And the series would be the third column of the H chart. We're in this middle column of the H chart. So the third column would look like this. The sums. First term's -1, or -2, sorry, or the 0 term's -2. So I'm not even going to use the 0 term. The first term gives you -1. -1 and 2 is a +1. 1 and 5 is a 6. 6 and 8 is 14. 25, 39. That's where these numbers are coming from. If we add them up. So the middle column is a sequence. The third column, the outside column of the H chart, is a series. And then here, since we backed up to the 0 term, we could say, all right, in function mode, I would just say y equals mx plus b, and I know the intercept's -2, and we said the slope was 3, 3x plus a -2, which is fine, but that's not the general term that we write this in sequences. That's here. So the general term for sequences, which will give you the same thing. If it's arithmetic, we say the first term plus n take away 1 times the constant difference. Now think about that. What does that mean? It means look at your knuckles. This is the first term, your first knuckle. Second term, third term, fourth term. So what happens? You're adding the difference in between the knuckles. So to go from the first term to the fourth term, you have these 3 valleys between your knuckles. That's 1 less than number of terms. Does that make sense? So if you wanted the fourth term, you're only adding the constant difference 3 times. So if I go up here and I say, all right, what does that got to do with this problem that we already did? The first term, a sub 1 is a -1, plus n take away 1 times the constant difference of 3. This and this are the same thing. Why? Because if you distributed this, you would get 3n take away 3, and you have a -1 plus that. Right? So you have a sub n equals 3n. First term's a -1. The constant difference is 3. Now we get negative 4 plus 3n, which is not what I want. What happened there? Say what? Oh, that's not going to do with it, though. Yeah, but that's not why I fouled it up. I'm saying the first term is negative 1 plus n take away 1 times the constant. Okay, so then this would be a negative 4. Okay, so that's why. Right? Negative 4 plus 3n. It's the same thing. Okay? That is explicit. That means your calculator is working horizontally. You put in, you want the 30th term, you just put 30 in. But if we're going to work recursively, the calculator is working vertically. And you can't get the 30th term without the 29th term. And you can't get the 29th term without the 28th term. It's like dominoes. So if we go to your calculator, now this calculator right here, I'm showing you the mid-grade version of this. So some people, if you have a skinny calculator, will have a different view than this, but this is like the mid-grade, the older TI-84s. So what am I going to put in there? I'm going to put in negative 1 plus n take away 1 times 3. Second graph, right? And if I go up arrow, I don't get a negative 4. Why? I get an error message. If I go back to y equals, I told the calculator that n min was 1. You can set it for 0. But I told her the first term was the minimum term. That is explicit. See, we're ignoring this u of n min line. Just ignore it. If we work recursively, we can't ignore it. So we type the same thing in the v line. We get down here and we say the v min is negative 1. And then what? Then we go up here and say, this is why, what am I going to say, McGarrigle? Oh, McGarrigle walked away from his laptop to go get it.
9.
Why is 6 afraid of 7? Correct. McGarrigle's awake. Why is 6 afraid of 7? Because 7, 8, 9. And if you look at your calculator, you see second 7, second 8, and second 9, where you have the U, V, and W. And that's where you're using those characters. So I want V. So I type second 8. And the calculator reads what comes after that as a subscript, even though it didn't write it as a subscript. And take away 1. Now I'm not multiplying by the constant difference. I'm adding the constant difference. Because I'm saying go to the term above it and add 3 to it. Second graph, the t-charts are the same. Okay? So that is a summary of what we did yesterday. We're moving on to geometric. So for a geometric series, sequence, sorry. What do you have? Explicitly, I have the first term times R, which is the constant ratio, caret n take away 1. Why? Because exponents are shortcuts for multiplication. And it's the same thing with my knuckles. I'm going to multiply the constant ratio 1 less than the term I'm trying to get to. Recursively, We identify G sub 1, and then we just multiply the constant ratio times the term above it. Okay? So let's look at this problem. 52. The second and third terms. So I'm over here. Second term and third term of a geometric sequence are 2.5 and 1.25. Which of the following is the first term? So I have n and I have g sub n. What would the first term be and why? Eddie, it is 5. Why? Because what are you doing? When you go from 2.5 to 1.25, you're multiplying by a half. So something got multiplied by 1/2 to give you 2.5. So that something would have been a 5. Or you could say, if I'm going up the t-chart, then instead of multiplying by 1/2, then I'm going to divide by 1/2. And dividing by 1/2 is the same as multiplying by 2. So let's go here. Go to your calculator. And I'm just going to take this stuff out. And you type in. Ready? You type the problem in, this problem from the textbook, explicitly in the U line and type it in recursively in the V line. Then you have to look, and your t-chart should match if you did it correctly. Okay? Now, here's what you have to notice. If you're working explicitly, that's what your calculator does in function mode. You don't need this mode. But the advantage of sequential mode is it works explicitly and recursively, simultaneously. Whereas if you're in function mode, it won't work recursively at all. So if you're working explicitly, you can leave this line empty. But once you go recursive, which is second 7, second 8, or second 9, if you don't have this cell filled in, where to begin, you're going to get an error message. Okay? You don't need it. See, it doesn't matter if you have it in there. If you put it in the U line, the first term's 5, it's not going to affect anything. But if you don't put it in the V line, you're not going to get anything. And what we're focused on is geometric, for chapter 9, not geometric sequences, but geometric series. So the geometric ones are more important than the arithmetic ones to your success in May. So I generalize this and go here. So I wrote this and said, suppose you did this. Suppose you started the zero term. Here's my first term, a sub 1. Add d, constant difference. Here's the generalization. What happens? This is like the knuckle example. To get the second term, I only add the constant difference once. So to get the 50th term, I'm only going to add the constant difference 49 times. But if you started at the zero term, you would have a sub 0. You can start at the zero term. A lot of times it's more helpful to the reader of your problem if you chose to start at the zero term. Well, then you would add the d times n times because you began at the zero term instead of the first term. Geometric, same thing. Ready? If I start the first term, I call that g sub 1, and I multiply r, the constant ratio. How many times? Once to get the second term, so it's 1 less than n to get the nth term. But if you start at the zero term, then you would have multiply rn times to get the nth term because you started at the zero term. Well, you got to look at this the first time because you can't assume whether something's at the first term or the zero term. You got to read the problem because that would foul you up. So a series is this. A series is adding the terms up. That's the third column of your H chart. It could be finite arithmetic. Arithmetic means you have a constant difference. Finite means you have a beginning and an end. Okay? Then this, a sub n, is that from what we just did. So where there's an a sub n in this expansion, I can write what it equals, and you get a second way to write it. That's just an algebra manipulation. This comes from Gauss, okay? So 450 years ago, Gauss is in grade school, and the teacher gives him busy work, not just him, the whole class, and says, all right, I got a headache. Give me the sum of the first 100 digits. Okay? Sum of the first 100 digits. So the kids don't have calculators, they don't have paper and pencil. They just have little slate boards. And all the kids are just sitting there going, 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. 10 plus 5 is 15. So the kid's up to the 5th term. He's got 15. Ready? And Gauss is just sitting there. The teacher's like, I already have a headache. Fred, get to work. He was working on it. He was thinking about it. That's what you have to do. Instead of just, as soon as you get a problem, what are you guilty of? Taking out your calculator and start typing stuff. You don't even read the question. Gauss read the question, and then he did this. He said the numbers I'm adding up are these. One plus 2 plus 3 plus up to 100. So he rewrote the numbers backwards. 100 plus 99 plus 98. Yes? Why? Because he added them up, and he said they're all 101s. How many 101s did he have? What? He had 100 of them. Because there's a one-to-one correspondence between the top line and the number of 101s. So to multiply by 100, you just add 2 zeros to the end. Except what? That's double your answer because he wrote the numbers twice. So that's how he got the 50-50 without doing the grunt work. So what's this? This is a generalization. Pair up the first number and the last number, multiply by the number of terms and divide it in half. Then, this is another way to write it algebraically. For a geometric series, if it's finite, now think about this. If it's finite, it's the first term times 1 take away r to the n divided by 1 take away r. We'll show you that. If you start at the 0 term, it would be that. But now what? If it's infinite, think about this. If it is infinite and the constant ratio is less than 1, then what would happen? Then this r, which is less than 1, when you multiplied that by itself an infinite number of times, it would go to 0. It would be 0. Then your numerator would be 1 times g sub 1. So the algorithm is easier for an infinite geometric series. Now, where does this come from? I thought I had it, but I don't, so I'll write it out. So you have this. You have g sub 1 plus g sub 1 times r plus g sub 1 times r squared plus so if we multiply everything by an r, this is g sub n. G sub n times r would be this number times r, g sub 1 times r. This number times r, g sub 1 r squared plus dot, dot, dot. What would happen? If we subtract them, we would have the first term would come down, everything would subtract to 0. We would have this last term here, which is g sub 1 times r to the n. Everything else inside subtracted. What's this? This is g sub 1. Subtract r times g sub n times r times g sub n. Factor it out. G sub n times 1 take away r equals g sub 1, subtract this, that's where this algorithm is coming from. Because you're not going to divide both sides by 1 take away r, and you get the expansion. Okay? That is if it is geometric. So let's look at problem number 10. I'll bring it up here. Or example 10, sorry. Show that this sequence converges. Converges, meaning if a sequence converges, the terms are getting smaller, it's going to 0. Cosine n divided by n. So it means this. That's 41. Sorry. Cosine n divided by n. So what's happening? The numerator is going between -1 and 1. The cosine can only go from -1 to 1. The denominator is getting larger without bound. So you have small over large. Small over large is equal to 0. Okay? So that's your model. Go to 41. If it's going to a number, not have to be 0. If it's going to a number, then it converges. Okay, so for 41, same thing. It's the sine instead of the cosine. So it's only going between -1 and 1. The denominator is growing without bound. Small over large equals 0. Ready? It's the limit. See, this is always going to have some, not always, but it's going to have a value. You can have 0 in the numerator. Sometimes when the sine's 0, which is the y value, which is at 0 and pi. But you're going to have some value here when the sine's not 0, except the limit of this thing is going to 0. And that's how we started the course. See what? Yeah, it always comes to limits, all right? So that's as far as we're going in 8.